Well, today we have a terrific presentation that I think is going to interest a lot of people, and we're very fortunate to have Amir Miodavnik, who is a board-certified pediatrician specializing in pediatric environmental health in the Department of Preventive Medicine at the Mount Sinai School of Medicine in New York City. He completed a pediatric environmental health fellowship and Master of Public Health degree at Mount Sinai under the mentorship of Dr. Philip Landrigan, which is a name familiar to many of us, I'm sure, for his really outstanding work in this area. Dr. Miodavnik's research has focused on environmental toxicant exposures and their potential adverse effects on children's neurobehavioral development. Together with his colleagues, he has demonstrated that maternal use of certain personal care products may have long-lasting consequences for child development. So I'm going to turn it over to Amir right now, and go ahead, please.
Thank you, Lynn. Hi, I'm Amir Miodavnik. Good afternoon. And I'll be discussing neurodevelopmental outcomes in children associated with chemical exposures occurring early in life. Now, a discussion of the neurodevelopmental outcomes associated with chemical exposures is replete with more questions than answers. This is in part due to the fact that little is known regarding the developmental neurotoxicity of many chemicals widely used today. One thing is certain: our chemical regulatory system as it currently exists is extremely ineffective in preventing hazardous chemicals from entering into commerce. Some of the most frequent questions regarding environmental toxicant exposures include: do the modest impacts on cognitive and behavioral functioning we observe in epidemiological studies have any clinical relevance? Are the long-term implications enough to justify changes in policy and drive innovations in green chemistry? Do the observational designs of most of these studies, which limit our ability to draw causal inferences, make them less convincing? Perhaps some of the answers can be found if we briefly review our current understanding of how these industrial chemicals and pesticides appear to affect neurodevelopment. We can start with an early example of a large-scale involuntary exposure. This so-called natural experiment occurred in the city of Minamata, located on the west coast of southern Japan. It was caused by the release of methylmercury into the industrial wastewater from a chemical factory from 1932 to 1968. This highly toxic chemical was dumped into Minamata Bay and bioaccumulated up the food chain in shellfish and fish, which when eaten by the local population resulted in widespread mercury poisoning. What was most striking, however, was the abnormally high frequency of cerebral palsy, mental retardation, and severe seizure disorders in children born to mothers who did not exhibit symptoms, and this was termed Minamata disease. The epidemic reversed the contemporary belief that the placenta would protect the fetus from toxins in the maternal bloodstream. We now realize that not only can exogenous chemicals pass across the placenta, but that they can have very specific impacts on the fetus, including neurotoxic effects depending not only on the dose of the chemical, but also on the timing of exposure. The gestational period in particular is exquisitely sensitive to the insults of environmental toxicants. Neurodevelopmental effects, however, are not limited to overt cases of clinical toxicity. In fact, many cases involve subclinical effects, which when factoring in a ubiquitous exposure can impact the entire population. A salient example of environmentally induced subclinical neurotoxicity was established with leaded gasoline. The phasing out of lead as an additive in gasoline began in the 1970s and was completed by 1991. However, knowledge of lead's adverse health effects was known for decades prior to its ultimate removal from gasoline. The concurrent decline in blood lead levels in children, as indicated by the yellow line, exceeded all expectations. And over the past 3 decades, the average blood lead level has fallen from 17 in 1976 to less than 2 micrograms per deciliter today. The economic gains that resulted from the removal of lead from gasoline have been estimated at about $200 billion for each annual birth cohort since 1980. Dr. Bellinger from the Harvard School of Public Health, in a recently published paper, concluded that the contributions of chemicals to IQ loss in children are substantial when considering the population impact. As public health advocates, we must look at outcomes at the population level and not base our conclusions on the magnitude of risk or effect size in any one individual. Assuming a mean IQ of 100 for a large population and a normal distribution, the tails of the curve represent those with an IQ in the gifted range and those with an IQ below the cutoff used to categorize mental retardation. A 5-point drop in IQ would significantly change the number of people in the tails of this distribution. For example, in a population of 100 million, a shift in the mean of 5 IQ points would result in a near 60% reduction in the number of gifted people and a proportional increase in the number of people with IQs less than 70. While the CDC maintains the blood lead level of concern at 10 micrograms per deciliter, existing data indicate that there is no lower threshold for the adverse consequences of lead exposure, and the impact on cognitive function may, in fact, be higher at levels lower than 10. Another example of subclinical toxicity has been demonstrated more recently by pesticide exposure. Recent studies provide data linking in utero exposure to organophosphates, a commonly used class of pesticides, and early cognitive development. 2 studies, one in an agricultural setting by Ashkenazi et al., and one in an urban setting by Rao et al., both found associations with prenatal exposure to the organophosphate chlorpyrifos and symptoms of pervasive developmental disorder and autism spectrum disorder in toddlers. 3 additional studies published in April of last year found decrements in IQ in adolescents associated with prenatal exposure. In one of those studies, by Bouchard, children in the category corresponding to the highest level of maternal exposure during pregnancy showed a 7-point decrease in full-scale IQ compared with children of mothers in the lowest category of exposure, an association of magnitude similar to that observed with an increase in blood lead concentrations from 1 to 10 micrograms per deciliter. Organophosphate pesticides currently account for about half of all insecticides used in the United States. The rate of production of new chemicals has grown astronomically since World War II and is predicted to double over the next 25 years. There are now over 83,000 chemicals registered with the EPA for use in commerce. 62,000 of those chemicals were presumed safe in 1976 and never required any further testing. These comprise most of the chemicals produced in highest volume today. Newer chemicals require a pre-manufacturing notice before entering the market. 85% of those notifications lack any health data because there is no minimum requirement to provide hazard data under current regulations. There are about 3,000 high production volume chemicals produced or imported in quantities of 1 million pounds or more per year, and nearly half of those have no basic toxicity information. Data on developmental toxicity is publicly available for fewer than 20% of these high production volume chemicals. The first piece of legislation to attempt to regulate this chemical boom was the Toxic Substances Control Act of 1976. Considered a landmark piece of legislation at the time, it has not been amended in over 30 years. As a result, about 1,000 to 2,000 new chemicals are introduced into commerce annually in the United States at a rate of 7 new chemicals a day. Since its inception 3 decades ago, EPA has only evaluated 200 chemicals for health concerns and has successfully banned or restricted the use of only 5 chemicals. TSCA, as it is known, requires EPA to establish on a chemical-by-chemical basis that an existing substance may present an unreasonable risk to human health or the environment. To assess this risk, EPA requires hazard and exposure data that producers are under no obligation to provide. This has created a disincentive for manufacturers to investigate their products' potential hazards, because although known hazards must be reported, ignorance of hazard is not penalized. TSCA has produced a chemicals market that favors existing chemicals over newer and potentially less toxic substances. As a result, the statute provides little motivation for industry investment in green chemistry. When we talk about adverse neurodevelopmental effects, we can more readily identify them as developmental disabilities in children, including learning disabilities such as dyslexia, attention deficit hyperactivity disorder, mental retardation, autism spectrum disorders, or cerebral palsy. We know that 10 to 15% of children in the United States have at least one type of disability, and secular trends in the prevalence of these conditions, such as autism, have only been increasing. Some of this can be attributed to increased awareness and better detection. Yet a recent paper by Hertz-Picciotto and Delwich argues that the increase in autism cannot entirely be attributed to better diagnosis and broader definitions. The National Academy of Sciences has recognized the role of the environment in the etiology of 3% of developmental disorders and in up to 25% of these disorders when considering an environmental trigger in conjunction with an underlying hereditary factor. Studies of the following list of environmental toxicants have found associations with neurodevelopmental disorders: lead, mercury, cadmium, arsenic, manganese, the polychlorinated biphenyls, organic solvents such as ethanol and toluene, organic phosphate pesticides such as chlorpyrifos, the organochlorine pesticides including DDT, phthalates, bisphenol A, the polybrominated diphenyl ethers, and the polycyclic aromatic hydrocarbons. In addition to these 13 chemicals, 200 chemicals are known to be neurotoxic in adults, and 1,000 are neurotoxic in animal studies, out of the over 83,000 chemicals that fall under TSCA's inventory. A group of these chemicals is known collectively as endocrine disruptors and are defined as hormonally active chemicals with the capacity to interfere with biological signaling mechanisms that govern development, reproduction, and immune function in humans. They have been receiving a lot of press lately because they are found in a majority of everyday consumer products, toys, and furnishings. Where else do they come from? Smokestack emissions, wastewater effluent, and pesticide residues. Suspected endocrine disruptors include some metals, plasticizers, certain medications, naturally occurring hormones such as isoflavones in soy, and of course industrial chemicals. Biomonitoring studies often find higher levels of these chemicals contaminants in children than in adults. When the Environmental Working Group, a nonprofit that specializes in research and advocacy in the area of toxic chemicals, conducted an analysis of the cord blood of 10 newborns, they found almost 300 different chemicals, an average of 200 per baby, with 154 different endocrine disruptors amongst them. This prompted the President's Cancer Panel to claim that children are essentially born pre-polluted. Why are children more vulnerable to synthetic chemicals in general and endocrine disruptors in particular? Well, first of all, pound for pound, they breathe, eat, and drink more than adults. They spend a lot of their time near the ground where dust and vapor settle. They spend a considerable amount of time putting their hands and other objects into their mouths. And their ability to detoxify and metabolize certain chemicals may be less developed. There's another source of exposure that makes them uniquely susceptible during key windows of vulnerability, and that is through the transfer of the maternal transfer during gestation. Whatever mom eats, breathes, and applies to her skin can be shared transplacentally or via breast milk. Even low levels of synthetic chemicals can disrupt the rapidly developing physiology of the developing infant. One group of endocrine disruptors is the polybrominated diphenyl ethers, or PBDEs, which replaced PCBs as fire retardants in the 1970s. They are found in polyurethane foam stuffing of furniture and mattresses and the plastic casings of electronic equipment. They are persistent and bioaccumulative. There's been a marked increase of PBDEs in human blood, breast milk, and other tissues as other persistent organic pollutants in our bodies have declined. In fact, women in the U.S. have up to 30 to 40 times the levels of PBDEs in breast milk compared to other countries. Why are we concerned with PBDEs? Well, they resemble the essential hormone thyroxine, or T4, which is critical to normal growth and brain development. Higher levels have been associated with reduced concentrations of serum total and free T4 in both rodents and humans. Low maternal thyroid hormone levels can potentially impair fetal brain development. Some studies have found association with PBDEs and neurodevelopment in young children due to both prenatal and postnatal exposures. Another class of endocrine disruptors are called the phthalates. They are plasticizers added to many consumer goods to make them more pliable, including vinyl curtains, tiles, rubber toys, as well as perfumes, nail polish to make the nail polish less brittle, shampoos, deodorants, and lotions to prolong the fragrance. Dermal applications of consumer products such as lotions, powders, and shampoos have been associated with increased urinary levels of phthalate metabolites in infants. The phthalates are also found in medical equipment used in the neonatal intensive care unit for catheters, tubing, and blood supplies, some types of food packaging material, and certain medications, such as Azicol for ulcerative colitis. Phthalates enter our bodies in the food we eat and the air we breathe. Two of the most common are DEHP, or di-2-ethyl hexyl phthalate, and DBP, dibutyl phthalate. We can measure their metabolites in urine. 99% of the U.S. population has measurable levels of these metabolites in their bodies. At Mount Sinai, at the Children's Environmental Health Center, we have found various neurodevelopmental effects related to phthalate exposure in utero, including decreased orientation and alertness in female newborns, decreased masculine play behavior, increased aggression, attention, conic disorder, and depression in boys, and decreased social skills in children. BPA, or bisphenol A, is the controversial building block of polycarbonate plastic containers and the epoxy resin lining most metal foods and beverage cans. But it's also found as a breakdown product of some dental sealants and as a coating on the thermal paper used for most receipts. Over 93% of the U.S. population has detectable levels of BPA in their bodies. Two published studies have found associations with prenatal exposure and maladaptive behavior in toddlers. The effects were seen mainly in girls. Exposure levels to BPA are commonly cited in the parts per billion. We can conceptualize a part per billion as half of a teaspoon of water in an Olympic-sized pool. However, is that enough to make a difference? And that has been an issue that has come up as the chemical manufacturers have argued the effects of BPA. Well, if the average amount of BPA found in cans is 25 parts per billion, and studies in animals have shown adverse reproductive effects at levels of 10 to 25 parts per billion, and in vitro studies have demonstrated cell signaling changes at levels in the parts per trillion. And if we take a more real-life comparison, there's about 20 to 35 parts per billion of the hormone estradiol in oral contraceptives, and even less in the NuvaRing contraceptive device. And that would help put things in perspective. The list of chemicals that could potentially impact neurodevelopmental outcomes is growing, and yet there is still no standardized and systematic approach in place to assess these important endpoints or to evaluate the chemicals that have the greatest potential for neurotoxicity. Terry Collins, the director of the Institute for Green Science at Carnegie Mellon University, was quoted as saying, "Endocrine disruptors put the welfare of our children on the chopping block, making them a top priority challenge for green chemistry." And Pete Myers, co-author of Our Stolen Future, which discusses many of the effects of industrial toxicants on children's health, was quoted as saying, "The current replacements for molecules like BPA were developed using the same flawed system that led to BPA, and often we know much less about their toxicology than the molecules we are seeking to replace." The path forward is for green chemists to explicitly design against hazards like endocrine disruptors and persistent bioaccumulative toxins. Avoiding hazard early in the design process before chemicals enter commerce differs from the current chemical management approach, which focuses on reducing rather than preventing chemical exposures. I would just like to conclude with one example of how the fields of environmental health and green chemistry are uniting to formulate new methodologies for identifying potential chemicals of concern. A recent meeting of the National Institute of Environmental Health Sciences scientists and leaders in the field of green chemistry in March of 2011 was titled Green Chemistry and Environmental Health Sciences, Designing Endocrine Disruption Out of the Next Generation of Materials. During the meeting, they discussed a newly developed screening protocol with a 5-tiered approach. It starts with the fastest and cheapest assays and progresses through more specialized tests to determine whether a new chemical has endocrine disrupting characteristics. The initial 2 phases rely on predictive computer modeling and high-throughput screening to quickly weed out problem chemicals. These tests are followed by more specific in vitro cell-based screening assays with a mind to refining, reducing, and replacing animal testing as much as possible. The protocol is intended to help green chemists establish a high degree of confidence that the replacements they are developing are unlikely to be harmful to humans or the environment. Thank you.
Thank you. That was great.
Sorry about the slide presentation. It was jumping ahead by itself.
Oh, no problem. I just wanted to say, I don't know if you can hear my phone. It's beeping a little, and that has nothing to do with anything. It's just losing its charge. So thank you so much for this presentation. There's so many interesting, I think the way that you put it together was really interesting for us to see, and particularly to reinforce our understanding of what the needs are in terms of green chemistry to be developing chemicals which can substitute and replace these chemicals. And even I would go as far to say, you know, on just the ones that we know, but as you pointed out, there are thousands of chemicals out there that have never been tested, and I think that represents a real challenge for us also. We're going to open it up now for questions. We have a lot of time for questions, and we really encourage people to jump in here. It's a great opportunity to talk with Dr. Yadovnik, and I'll just start, raise your hand and type your question into the little question box, and we will be happy to call on you. Okay. I have a hand up from Stell, but I need you to type your question into the question box down at the bottom. We see your hand is up, but we're going to do everything by answering questions that are typed into our box. So if you could please do that, we will right away go to answer your question. So can you talk to us in the meantime while we're waiting to get people to type their questions in? So what is the direction of the research now? Where do you see going with this in the future? I think I just came from a conference on looking at brominated fire retardants, and of course that includes some of the chemicals that you were talking about. So can you give us some idea of where you're going in the future with your research and what kinds of new issues are being raised by the current research?
Sure. Well, initially, about 10 years ago, the idea of a large-scale study to look at a wide range of environmental pollutants became a reality, and it was called the National Children's Study. The National Children's Study was supposed to follow 100,000 children from before birth and even before conception through the age of 21, and it was supposed to measure many different environmental exposures, both in the home and also test blood and urine and other tissues and placenta for various exposure levels. Recently, the National Children's Study has come up with some problems in its implementation, and it may not necessarily evolve as it was initially intended. We do intend to continue our smaller studies. These are the cohort studies where we follow the children from before birth, measuring levels of exposure in the mothers, and then testing the children later in life. And there's a handful of those studies, and most of them I covered in regards to the chemicals that I mentioned. They're all mentioned in the presentation. There are a few more studies that I didn't mention regarding phthalates, where they found in cross-sectional studies phthalates associated with symptoms of ADHD and with IQ as well. But we intend to, the problem is that while these are the best kind of studies we can perform, because we can obviously do experimental studies on children, we're stuck with observational studies. And one of the problems is that it's difficult to get funding for some of these studies, and they're very difficult to conduct because you do have to recruit mothers who are pregnant and then test the mothers and then stay in contact with them for years. But these are right now our strongest tools that we have in our arsenal to demonstrate the toxicity of these chemicals. It's also one of our weaknesses, or Achilles heel, because again, you cannot demonstrate causation through these observational studies. You can only demonstrate associations. But we are also looking at Mount Sinai. We're looking at chemicals including the parafluorinated compounds. We're looking at perchlorate, which is released from rocket fuels, which is also highly pervasive in terms of water contamination. And we're looking at other types of the effects of organophosphate pesticides on different parameters as well, such as birth weight, birth outcomes, and things of that nature.
Yeah, thank you. That's some of what you're saying is really reminiscent of the early studies by the Jacobsons on fish eaters.
Yes, yes.
Children in the Great Lakes.
Exactly. The Jacobson studies, and when they were looking, those were specifically looking at
PCBs.
both PCBs, and then even before PCBs primarily, and then the studies also that were looking at methylmercury in some of the populations from fish consumption. Those were the large studies that really initially drove home, similar to some of the lead studies, but these were the large studies that drove home the impacts of these chemicals during gestation. And these children were followed for long periods of time, and definitely showed effects that could be associated with early exposures. But yes, that is the same type of study that we're trying to replicate with our cohorts as well.
I hope you are able to do it. I have several questions here. The first one, I'm going to read it to you. I'm not quite sure what he's asking that's different than what you've been saying, but he asks, first he says, thanks for a great presentation. What is being done to address intergenerational aspects and increasing sensitivities?
Yeah, what we're finding is, especially with the endocrine disruptors, is that there are transgenerational effects. We're seeing not only that they can impact the first generation, the children born to the mothers who are exposed, but now we're seeing effects in subsequent generations, especially if chemicals can have effects on the germline of the fetus. And we're seeing this not only the second generation, but sometimes into the great-grandchildren, and the great-great-grandchildren might have effects. And the current thinking is that some of this is secondary to epigenetic changes in the DNA that these chemicals can also produce. So epigenetics is becoming also a topic of great interest to people studying chemical pollutants, because it now seems like this is yet another effect modification that can occur that has not been used in risk assessment. Most of the studies looking at the basic toxicology effects look at gross effects on the animals or the offspring, but have not looked at different things like changes in methylation patterns and histone deacetylation that can occur as a result of these chemicals. And we're finding that some of these chemicals do actually induce some epigenetic changes. One chemical that has been around since the 1930s and was used in the 1950s through the 1970s, diethylstilbestrol, is a prime example of this. It's known to cause clear cell vaginal adenocarcinoma in the daughters of children exposed during pregnancy. And now the National Cancer Institute is looking at effects in the grandchildren as well, seeing that they are also demonstrating adverse effects from prior exposure in the grandmother. And so this is definitely an area of hot area of interest in environmental health, are the epigenetic effects.
Can you just briefly give a definition of epigenetic effects?
Yeah. Epigenetics are changes that do not directly change the DNA. So you're not deleting or you're not having alterations in the actual DNA itself, the base pairs, etc. But it's changes that modify the DNA by either adding what's called a methyl group to a base, or taking a methyl group from another structure called a histone. And these are actual structures that the histones are actually what allow the DNA to become compact and inside the cell nucleus. And so it's not actually part of the DNA, but we're noticing that when you change these substrates, or the histones, or if you methylate, which is adding a methyl group to one of these base pairs, it can affect the transcription or the messages that the DNA are coding for. So if you, for example, methylate a certain part of the DNA that is supposed to code for a gene that is important in in some reproductive endpoint, for example, that gene will not go on to produce the protein that it's supposed to produce, and that can have downstream effects on the organism. So these can switch on and switch off the coding and the production of proteins without actually changing the DNA structure, and that's why it's called epigenetics as opposed to genetics, because it's things that are associated with the DNA, but it's not the DNA itself. And this is actually, we're finding that this is actually why some evolutionary changes may occur faster than changes to the DNA, because now we see that these epigenetic changes are heavily influenced by environmental exposures. So these things can change, whereas DNA does not change very easily. These epigenetic changes can occur fairly rapidly as a result of exposure to an environmental toxicant, for example. And these can carry on from generation to generation, much like DNA. So you can see the effects of a chemical through different generations. I don't know if that clarifies it a bit.
That's very helpful. We have a lot of questions, so I'm going to try to whiz through these. Is there anything that can be done nutritionally to reduce the impacts of these chemical exposures?
Nutritionally, a lot has, for example, with epigenetics, one of the key nutritional factors that seems to influence the epigenetics as a result of some of these chemicals is folic acid. So folic acid seems to be, we found that that folic acid seems to influence the level of methylation, for example, due to these chemicals. And so one of the recommendations now is that women have sufficient folic acid both before birth, before conception and during during the first months of gestation. And it's actually been shown to reduce the incidence of things like autism, for example. But in terms of nutritionally, I mean, for example, decreasing exposure to pesticides, it's been shown that children who were fed organic fruits and vegetables did have lower levels of pesticides in their metabolites in their urine. So nutritionally, one of the things is to avoid certain pesticides, or to try to encourage organic foods. Obviously, this isn't always feasible because of the expense of organic foods. So sometimes we recommend, there's a list on the Environmental Working Group site, website of those fruits and vegetables that have the least pesticide residues versus those that have the worst pesticide residues, and to try to at least reduce your pesticide load.
So this is Clinton. Can I follow up on that question? I know Stella had asked a question, and I think that the question may be related to if you already have toxins in your bloodstream, and I think of particular interest to Stella would be lead levels, for example, in your blood. Is there anything that you can do nutritionally to help you reduce that body burden?
Yes, for lead, you want to maintain your iron status. So it's shown that iron deficiency actually increases lead absorption. And so one of the first things we check in children is to make sure they're not iron deficient. Calcium seems to help also reduce the amount of lead that's absorbed in the bone. So you want to maintain your calcium levels as well. So we encourage children to, who have lead lead levels that are higher than 5, because for us the level of concern is definitely less than. We do not base it on the 10 that the CDC bases it on, but levels of usually 5 and above indicate some kind of lead exposure, and we encourage calcium, and we also check iron levels to make sure the child is not iron deficient. That's in particular with lead. Other substances, have shorter half-lives. So, for example, with mercury, there's not much nutritionally you can do. You would just avoid the products that are higher in lead and allow your body to get rid of the lead or the mercury that's already there. For some of the plastics, for example, phthalates, which are so ubiquitous, the phthalates, because they're found in so many products, it's really hard, other than regulating from a top-down approach and getting rid of phthalates, to avoid phthalates altogether, because they find their way into food, and the primary route is ingestion from dust and from contamination of food. Other things you can reduce for the persistent or bioaccumulative substances like the polybrominated diphenyl ethers or the polychlorinated biphenyls, the PCBs. They're found in fatty foods, so you want to avoid any type of fatty meats or fatty dairy products. That's one way to reduce exposure to those chemicals. But again, they do find their way into our diets, and it's very hard to avoid them altogether. Lead is one of the few that there are some dietary modifications you can make. But again, the only way to reduce your lead level is to find the source and to prevent further exposure.
Thank you. Our next question is, in my work in helping folks to reduce their use of pesticides, I hear over and over again how there is no evidence that pesticides cause any health problems for children or adults. What is your recommendation for responding to these assertions when the evidence seems overwhelming that it does cause harm?
Again, this is a problem we always encounter because we cannot conduct experiments in children. We cannot, expose one group of children to pesticides and another group, withhold the exposure and follow these children. So the best we can do is to actually look in the, at levels that are already present in the body, and see if there's any associations with later on development. And there are many problems with those types of studies because they are not the ideal study. The ideal study is the experimental study, the double-blind clinical trial, which we can do for drugs, but we cannot do for environmental toxicants. So one of the industry definitely does try to point out that our studies not only, sometimes the findings are modest findings, several IQ points here or slightly lower scores on a certain mental developmental index on a test. But these are the tools we have available to us. And I mentioned 3 studies that actually were published simultaneously in the Environmental Health Perspectives Journal in April of 2011, all 3 of them from 3 different centers using the prospective cohort study design found decrements in IQ points in children who had higher levels of prenatal exposure to pesticides. So there is, and we know that the organophosphate pesticides can be toxic. They were developed to be toxic. They were actually developed initially as to be used in toxic warfare, and then they were modified to be to kill insects. And so we know that they're toxic. It's now that we're finding that the levels lower levels of exposure are also detrimental. Before there were cutoffs that were based on toxicological studies in animals, and now we're trying to base the levels, acceptable levels of intake on the epidemiological data because we're seeing effects at much lower levels than you would see in animal studies. Because we're looking at much more refined outcome measures. We're looking at, you can't measure IQ in a mouse. So these are the things that we're seeing, even and as I mentioned, even 5 IQ points can have, with a ubiquitous exposure like pesticides, can have a pretty substantial effect on the population. So there is definitely, especially for pesticides, there is a large body of literature showing that they are neurotoxic and that low levels can have effects. So it's, you can present them with the data that I included in this presentation.
Thank you. So we have another question from a student at McMaster University who's in engineering and public policy. He says, I'm looking at EDCs in wastewater, endocrine disruptors, in wastewater, and was wondering what work is being done to understand the most prominent contributions to endocrine disruption via different media, inhalation, ingestion, water, and skin. Do you have an idea of what would be a safe limit for exposure to the fetus?
With respect to, was it PCBs? Or
no, endocrine disruptors.
Oh, just in general.
Yeah.
It depends on the endocrine disruptor. And it depends on the. Now we're finding more and more routes of exposure. For example, for BPA, for bisphenol A, initially it was thought the primary route of exposure was ingestion through polycarbonate plastics and through the lining of cans. More recently, we've found that exposure can also occur through these receipt papers, and that may contribute not only through maybe absorption through the skin, but also by people touching these receipts and then somehow transferring that to food. So right now there are no it's very difficult to say specifically what levels are, which source of the exposure is the highest. We feel that ingestion is the highest source of exposure, or contributes the highest to the exposures for, at least for BPA, PBDEs, PCBs, phthalates, and certain of the organochlorine pesticides like DDT, which is still found in our bodies, even though it's been banned for almost 30 years, or at least 30 years. because they're so persistent. But I think each endocrine disruptor, it also will depend on the mechanisms by which they are having their effects. And that's an area that's still new, is trying to really pinpoint what effects these different endocrine disruptors are having. We know that BPA, for example, is considered a weak estrogen, but we don't know if that is how it is having its primary effect, and it may be through other routes that have yet to be investigated, for example, through epigenetic effects that have not been clearly delineated. So it'll depend on the mechanism as well to determine the safe levels, because we're finding that the effects are occurring at lower and lower levels, even than the safety levels that have been established based on, again, safety levels now are based on toxicological studies in animals. At least for the endocrine disruptors. So until we can modify that thinking and see them as having effects at lower levels than we would see in animal studies, we don't know, we're not going to see reference range or safe reference concentrations or total daily allowable intakes like we do for some other chemicals. There are set standards. I mean, 50 micrograms per kilogram per day is the established level for BPA, but we're seeing effects at much lower levels. So, the question is, when are we going to move the levels of safety down? And that will definitely have an impact on, chemical production, because we're going to have to reduce the BPA exposure to begin with, or take it completely out of the pathway of exposure. I don't know if that answered the question, but I think the question was of what levels of endocrine disruptors cause effects?
Yeah, I think it was, is there an established...
There really aren't for many of them.
Do you have an idea of what would be a safe limit for exposure to the fetus?
Yeah, I mean, for the fetus, it's really, it's difficult to say. A lot of the studies, again, draw from the animal literature, and so we don't necessarily trust in those levels so much because they're not based on human epidemiological studies. Like, for example, the current level for mercury, which is not necessarily one of the endocrine disruptors we discussed, but it was based on studies from the Seychelles, or not from the Seychelles, from the Faroe Islands in a human cohort. And so the older chemicals are based on human data, but for the endocrine disruptors, there are no human studies for which they're basing their safety levels. So until we are using levels that incorporate these human studies, there are no, we can't be sure about the safe levels or the levels that have been set for safety. Like I said, the only one I'm familiar with is for BPA, intake of BPA, and we already know that we're seeing effects at much lower levels of exposure.
Thank you. We have a couple of more questions. I'm going to try to squeeze them in, but I wonder if we can impose on you for me to email you those in case
of course.
you don't.
Of course.
That'd be great, and then we'll post them on our website, folks. So let me just rush through the next question. Thank you. EPA released its first 83 work plan chemicals on March 1st, prioritizing chemicals for further evaluation and action with existing information. Do you have any comments on EPA's approach? And a similar question was also raised, well, related. Have you been involved in the development of screening tools for endocrine disruptors, which I know that EPA is also involved in? Can you talk more about that? Also, can you talk more about your work looking at the impacts of phthalates, which particular phthalates were associated with the behavioral effects in your studies. But we'll start out with the question of the 83 chemicals.
Yeah, I think that, I mean, it's taken, I think, the EPA maybe a decade to come up with this list. I think when they, you know, in particular with as far as the endocrine disruptor screening program that they developed as far back as I think it was 1998 or sometime around then, and it took over a decade to come up with this priority list, and I think primarily they're pesticides. So it's still, and it's just the list. So it's, you know, it's it took them that long to come up with the list. You know, in terms of what the next steps are. You know, the next steps. I mean, it is a step, but it's definitely at this pace. You know, by the time that we determine which chemicals need to be evaluated and if necessary discontinued, it's going to take a very long time. And so we need something more like they've developed in Europe, the REACH program, which was started in 2006, which already has a priority list of 30,000 chemicals. And a list of chemicals of concern, 10,000 chemicals of concern. And so that type of legislation is what we need. The EPA, it's taking far too long to come up with a list of 83 chemicals. And again, I think these are primarily pesticides. And in terms of the phthalates, the thinking is, again, the mechanism underlying how the phthalates are having an effect is not clear. They are considered anti-androgens, meaning that they block the hormones that are involved in masculinization, but they also seem to affect thyroid hormone. And one of the concerns that we have is that phthalate levels in moms, if the levels are affecting thyroid hormone, that can have a significant impact on the developing fetus, which is completely dependent on the maternal thyroid hormone in the early part of gestation, and almost and still depends on it up through birth. So those are two of the mechanisms, either an anti-androgenic effect or blocking somehow testosterone production, or somehow affecting the ability of thyroid hormone to have its effect in the brain. Those are the areas we're looking at for phthalates, but the exact mechanism is not certain for phthalates, how they would be causing the problems with behavior and socialization. I don't know if that answered that question, or those two questions.
Yeah. Oh, I'm sorry. Go ahead.
I don't know. Yeah, I mean, the EPA, you know, again, the EPA is extremely slow in regulating these chemicals, and at the current pace, we you know, unless some new legislation is passed, which was presented or introduced into Congress this past fall to modify the chemical the chemical regulations policies in this country to be more like the ones in Canada and Europe, we're not going to get very far. And it's going to take a very long time if we continue to do things chemical by chemical. Because we know that not only are there additive effects from chemicals that have the same mechanism, like the different types of phthalates, but there's also the cumulative effects from the different types of exposure. So we're only studying inhalational exposure or ingestion, but you have to factor in that you can get phthalates from ingestion, inhalation, dermal exposure, and that, to have to study every different pathway of exposure and do it chemical by chemical will just take too long to have an impact.
Thank you. This is a great discussion. I wish we could continue for a lot longer, but we're actually at 3 o'clock already. And I just wanted to mention one of the questions that we didn't get to was where can you find some educational information and materials about this. And I wanted to give everybody the website of the Environmental Working Group that was mentioned, www.ewg.org. And you can really find a lot of the information that you're interested in on that site. So
Yes,
we will
definitely.
post on our website in the resources section some other places, the Campaign for Safe Chemicals, and some of the other full resources that are available for that kind of information that you can either get or you can download and print out yourself.
Yeah, another one is Our Stolen Future is another
Right.
website that
Yes,
has a lot of information
Right.
on endocrine
Right.
disruptors.
And also the Endocrine Disruptors Exchange, which is Theo Colburn's
Yep,
site,
exactly.
and she's been a speaker actually in our here.
Yeah, she's
So-
the one who coined the term. Yeah.
Yeah. Thank you so much. This was a Clinton.
Sorry, this
Clinton,
is
are you trying Clinton?
Yes, I was wondering if I could impose on our presenter and just ask one more question.
Sure.
I was reading the other day about this, at least the initial discovery that neurotransmitters such as serotonin may actually be synthesized by the placenta itself
Mm-hmm.
and influence the fetal brain directly rather than having via the mother's
Right.
neurochemistry.
Right.
So I assume that's going to open up a whole bunch of new ways in which chemical exposure in the mother could affect brain development in the fetus.
Yes, exactly. The placenta is, I mean, now we're just now starting to study the placenta and the ways it itself produces a host of effects on the fetus, in its own right, and how the placenta also influences whether the endocrine disruptors, how the endocrine disruptors interact with the placenta, and also if the placenta itself is protective in any way or somehow exacerbates the effects of endocrine disruptors. So we're collecting placenta samples here at Mount Sinai as well. It's part of our new placental repository, because it's definitely going to be, the placenta will be a window into how the fetus develops. So it's an important thing to examine is the placenta, for sure.
Thank you. Thanks.
Thank you so much. I'm going to have to draw our webinar to an end, but we will follow up on the questions that were asked and see if we can get some more information as well on our website. Thank you again, Dr. Miodownik, and thank you to everybody who signed on.